Hello everyone. Today we will be covering some more problems on graphing functions. So let's read over the problem. We have f of x again, same graph we've been using before. Well, the only difference is that now we want to, for part A, evaluate f of 2x for the following values: x equals negative 2.5, x equals negative 0.5, x equals 1, and x equals 2. We want to also name 4 points on the graph of y equals f of 2x. For each of these points, name a graph on y equals f of x. So I made this table kind of reading a little bit into the problem already, like ahead of time. So I'm just going to call this my column for points on f of x, and then we have our points on f of 2x, and we'll fill out the other parts in a second. But alright, let's get started. So we're going to start with x equals negative 2.5. Since we're finding f of 2x, what we'd like to do is say we have f of 2 times negative 2.5. Well, 2 times negative 2.5 gives us negative 5. So what we're really looking after is f of negative 5, which is equal to positive 7. Because if we go to negative 5 on the x-axis, the point corresponding on f of x would be 7 on the y-axis. Okay, now let's carry on. F of 2 times our next x value, which is negative 0.5. And 2 times negative 0.5, or simply negative 1/2, is f of negative 1. Now, that would have a corresponding y value of, well, negative 1 on the x-axis corresponds to positive 4 on the y-axis, that point right there. And notice we're finding right now these are points on f of x. So let me fill this out as we're going. We have already found that negative 5 has a y value of positive 7, and that negative 1 has a y value of 4. Now let's keep going. After that, we want to do f of 2 times, and then we have x equals 1. 2 times 1 is 2, so we want to find f of 2, which gives us a y value of positive 1. So when your x is 2 on f of x, your y value is 1. Now, if we were to keep going for the last one, f of 2 times 2 is now our x is equal to 2, which is f of 4, which is equal to 1, 2, 3, 4, and our y value is a negative 1. So we have 4 comma negative 1. So what are the points on the graph of f of 2x that corresponds with f of x? Okay, so what that means is, let's look back at what we did in part A. Notice the x values we plugged in are different from the x values that we ended up using to find the points on the graph. But in terms of our function f of 2x, those are the x values we are going to use. So, like for instance, x equals negative 2.5 found us a y value of 7. So on f of 2x, we have negative 2.5 comma 7 as a point. And let's label that in red. So let's go to negative 2.5, and then we would go up 7 spots. Right there. And then we plugged in x equals negative 0.5. That would be what we did right here. And we found that the corresponding output was negative 4. So our next point is negative 0.5, comma, positive 4. So on our graph, we go to negative half and go up 4 spaces. That would be right there. In fact, let me clean off some of the board real quick to make everything look a little bit neater. Okay. So now the last part, or not the last part, but for the next one, we found that when x was 1, y was equal to 1. And when our x was 2, our y was negative 1. So let's plot those points. That would be here and here. Interesting. So from what it seems like, it seems that our points are being halved in their x values. We went from negative 5 to negative 2.5, negative 1 to negative 0.5, 2 to 1, 4 to 2, halving each time. So in order to complete the graph, I'm going to take each x value, like this point here, and halve that distance. So this is 2.5. So that would give us 1 1/4. And I think that should be enough for us to complete the graph. We're going to do the line in red. It's going to look like so. And, well, the end point would be at 1, 2, 3, 4, 5, so 2.5. So right there. And that is our new function. So the red is our f of 2x. Yikes. All right. Now, the next one it wants us to find for part B is f of x over 2. So this is going to be my f of x over 2. Now, if multiplying by 2 caused it to shrink in value by half, I wonder what the x over 2 will do. Probably double it if I were to suspect. So let's try some different values. So the basic gist of this is that you have in our original function, let's say our x value was negative 5. And when we found it for 2x, we had negative 2.5 because 2 times negative 2.5 is negative 5. So what we should be asking is what value, when cut in half, will get us negative 5. Now, that might be, you might have some good arithmetic skills so you can figure it out right off the bat, but if you wanted to do it algebraically, set it up like this. X over 2 equals negative 5, and then all you have to do is multiply by 2 on both sides to solve for x to get that negative 10 is going to be our new x value. Negative 10. And I should get the proper y value of 7. Now, let's just double check to make sure if I did the work right. F of negative 10 over 2. Well, negative 10 over 2 is negative 5, which we know is 7. That's why we kind of are working backwards to get the proper x value we would like for our new function. So, where can we go from here? Well, now I want an x value that when plugged into f of x over 2 is going to give us negative 1. Well, negative 2 over 2 is negative 1, so that should be my x value, and it will correspond to the y value of 4. And again, you can plug these back into the function to double check. Negative 2 plugged into f of x over 2. It'll become f of negative 1, giving you the proper y value of 4. Okay, now what can I plug in to get 2? Well, 4 divided by 2 is 2, so I'm going to have 4 comma our output of 1. And then we can see the pattern. Yes, we are indeed doubling the x values. So let's plot all those points and see what our graph looks like. We have negative 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be where negative 10 is, and then up 7. So right there. And continuing on, let us plot negative 2, comma 4. Be right there. Then we have 4 and positive 1, so 1, 2, 3, 4, and up 1. And then we have 8 and negative 1, so 8 and then down 1. And let's move some of the other important points, like from here, if we're doubling the distance and it's 2.5, then we're going to be at 5. So 3, 4, 5. And then the end point is 5 away, right? 1, 2, 3, 4, 5. So we want another 5 out there. Okay. Now let's connect all the lines on our graph. So we got from here to here, then from there to there, and then all the way across to the endpoint. Now we can see that this purple function that represents f of x over 2 is very widely stretched out along the x-axis. In fact, double the length. So that is very interesting. It seems to work in reverse to the vertical compressions and growths. Now let's try out the last one, which we will do in black. F of negative x. Okay. Well, what value can I plug in so that I get negative 5 as my input into the function? Well, that would mean that x would have to be 5. And that my output would therefore be 7. And we're just basically flipping the values. This one's probably the easiest one to work with. So that's negative 2 comma 1 and negative 4 comma negative 1. Now let's graph those points and see what we got. So we have a positive 5 and then up 7. So I believe that's it. Then, actually, let me do this part in green because it's going to mix too much with the original function. Then we have 1 comma 4, so positive 1 and then up 4. From there, we have negative 2, positive 1. And from there, we have negative 4, so negative 1. And let's take some of these endpoints and move them over. So this point, since it's negative 2.5, it go over to positive 2.5 over here. And your endpoint over here is 5, -2. So we want to go to 5 and then, yeah, -2 right here. Now let's connect the graph. So here we go. It should look like such. And we get that graph right there. So hopefully we've had enough time to look at these other graphs. I'm going to get rid of them so we can more clearly see the effect of the neon green one. Almost there. And let's just erase for good measure. Now, what's going on with this graph? Well, all that happened is we took all of the x values and reflected them over the y-axis, or take every point really, reflect it over the y-axis. So for instance, this negative 5,7 became a positive 5,7. So we get a basic reversal of the original graph, which makes sense because when we were doing the vertical shifts, negative f of x was a vertical reflection over the x-axis. Now we have our horizontal reflection over the y-axis. So with all that being said, let's look at part C. I'm just going to move this around. Okay. And, alright, part C says, suppose f, capital F, is a function. How is the graph f of x related to the graph of f of kx, where k is positive? So if k is greater than 1, the graph will shrink by a factor of k. That's the first thing we know. Because again, 2 is certainly greater than 1, and look at our x values. They're all shrinking by that factor of 2. Or being halved, I should say. I should really say by a factor of, if I'm going to be nice and proper, 1 over k. Now, what happens if k is between 0 and 1? So if k is between 0 and 1, the graph will enlarge by a factor of k. And then the last thing we know is that if k is negative, then the x values will reflect over the y-axis. Not even x values, the points. So that's an easy way to tell just by looking at what's happening in your function f of x. Without even having to do any calculations, really, you can easily figure out how the graph will be affected.